Hi everybody, I'm Dr. Chad, and welcome back to my course on quantitative research for qualitative researchers. So far, we've done a lot of background work, learning basics of data visualization, how to ask a research question, and how to operationalize our variables. But now I want to start going through how to do basic analysis and start walking through some statistical analyses with increasing complexity. We've already done univariate analyses in the previous videos, answering questions like what percentage of names in the baby names dataset are male or female, and what were the biggest gender-neutral names of 2017. These lessons focused on data viz and important skills there, but they were actually answering research questions and doing work communicating analyses with a single variable, and you didn't even know it. That's what my Meemaw used to call mixing the kale in with your smoothie. Today I want to branch out a bit and start some bivariate analyses, or analyses with two variables. We did a little bit of that previously by using a line graph to learn when the most children were named Beyonce, but today we're going to do a bit more of a practical analysis. So with that out of the way, let's go ahead and get started. Like all good research, we're starting with a solid research question. This comes from a very real company asking me to do some consulting then on their new product, Jira Misu. Do not question, this is obviously a real product with a real company. Our friends at Jira Misu asked me to analyze an A/B test they conducted. They apparently have really smart engineers who can set up a great A/B test, but no quantitative researchers on their team. So that's where we come in. And this is perfect because it sets up a great lesson on bivariate analysis. A/B tests are a great example of this because there are one variable we want to measure and one variable that changes things, a control and an experimental variable. The example here is conversion rates, or something like people who sign up for a product, or hits per month or whatever. Our friends at Jira Misu have the basic version of their software, Jira Misu Espresso, and they want to see if users would be more likely to convert to a premium plan, Jira Misu Layered, if they added new functionality where users see a cloud of espresso powder shoot up in the air whenever a project is completed. It's a pretty cool feature in my mind. I'm curious to see how it will work. We'll do a full lesson on A/B testing later, but we probably should talk about what that means before we get too far into it. An A/B test is a simple yet powerful experimental method used to compare two versions of something, such as a web page, a marketing email, or a product feature, to determine which one performs better based on a specific metric. The idea is to split your audience randomly into two groups. Group A, the control group, sees the original version, while Group B, the test group, sees the new or modified version. By tracking how each group responds, you can measure the impact of the change. Random assignment should hold all other variables constant between the two groups, so the only difference is which version they get. There's a lot more to it, and be on the lookout for a full video on this later, but that's enough background for now. Let's go ahead and get back to the main stage. So we have our research question. Are users more likely to convert to the premium plan if we add this celebration when a project is completed? We also have our outcome variable, conversion to the premium plan, and it's coded as yes or no dichotomous variable, one with two options. We also have our explanatory variable, included in the experimental group, coded as yes or no. This covers all our bases from the previous lessons, so I'm really excited to get into the analysis here. So with all the bases covered from the previous lessons, I also want to point out we have an impactful research question here with a clear value to the business, which is something to think about whenever you're working as a product researcher. How can the business apply the output of what I'm doing to help make decisions? In this case, we'll be able to give them good evidence as to whether or not this new feature is actually worth putting into production, which is very exciting. Let's start as we always do, loading the important libraries into R. For today, we'll be using base R for loading our CSV, using ggplot to graph, and maybe some light data processing in dplyr. So just loading the tidyverse should be enough. Interns, go ahead and do that right now. Okay, easy enough, well done. Now, we have a problem because Jira Misu's lawyers just reached out to me and told me I'm under a very strict non-disclosure agreement for their very real company. So instead, we're gonna have to simulate a data set in R that would recreate an A/B test with a statistically significant difference between groups. Obviously, don't do this in real life. This would be beyond anything you should do. But for teaching purposes, this is more than fine. Interns, go ahead and write up a script that gives us a sample data set. Okay, this looks great. We're going to draw a sample of 1,000 people per group. The control group we drawn from the binomial distribution with a conversion rate of 0.10 or 10%. The experimental group we drawn from the binomial distribution with a conversion rate of 0.14. We're going to turn that into a data frame so we can do our own analysis on this. Life is good. So time for our analysis. We're going to use something often referred to as a t-test or a difference of means test. You'll probably most commonly hear of this as a t-test, but difference of means is a much clearer title, so let's go ahead and use that for a minute. If you're interested in the math of a t-test, this is not the right video for you, but there are plenty of places that will help you learn to calculate them by hand like it's 1999, if that's what you're looking for. So I just made a joke about learning the math of a t-test, and I stand by it. I do, however, think it's important for people to understand the intuition of what a t-test is, so I'm going to spend a minute walking you through that here from the lounge. How do we figure out if two groups are truly different, or if the differences we see are just random chance in sampling? That's where the difference of means test, or a t-test, comes in. It's a powerful statistical tool used to answer this question in fields like science, business, and medicine. So let's break it down step by step. The first thing to understand about a t-test is that it starts with something called the null hypothesis. The null hypothesis assumes there's no real difference between groups, that any difference we see is just due to random variation. For example, if we're comparing test scores from two classrooms, the null hypothesis would state that the average scores of each classroom is essentially the same. We also have an alternative hypothesis, which says there is a meaningful difference between the groups. The goal of the t-test is to determine whether we have enough evidence to reject the null hypothesis and lend support to the hypothesis that the two groups are different. To start, we compare the means of our two groups. The mean, as you may remember, is simply the average value. It measures what's typical for each group. For example, imagine classroom A has an average test score of 85, while classroom B has an average score of 78. Those averages give us a starting point for comparison. In real-world scenarios, these groups could represent anything, like comparing customer satisfaction scores between two stores, average blood pressure levels between patients receiving different treatments, whatever you want it to be. If there's two groups in random assignment, you can have an A/B test. The mean helps us summarize each group's data into a single number. But here's where things get interesting. Averages alone don't tell us everything. We need to ask, are these means different enough? That's where variability and standard error come into play. The standard error measures how much variability there is in our data set. It's essentially a measure of how precise our means are as estimates of the true population averages. If there's a lot of variation between the groups, like students in classroom A having very different scores from each other, then even a big difference between the means might not be statistically significant because it could just be random chance. On the other side, if the students in classroom A have very similar scores, then even a small difference between the means might be statistically significant because the variability is much lower. The combination of how different the means are and how much variability there is in each group, or how high the standard errors are, lets us decide if the two groups are different enough to reject the null hypothesis and declare those differences statistically significant. What is statistical significance? Great question. Well, we find this by calculating something called a t-statistic, which measures how large the difference between the means is relative to their standard errors. The math is not important here. There's other videos you can use to learn that, but the basic logic is that the higher the difference and the lower the standard error, the higher of what is called the t-statistic. We can then apply this t-statistic to a probability distribution to help us determine a p-value, which is a probability that tells us how likely it is our observed difference happened by random chance. For example, a p-value of 0.4 means that our observed difference had a 40% chance of happening by just random sampling. But a probability of 0.01 means it only had a 1% probability of happening by chance. If this p-value is smaller than our chosen significance level, usually 0.05, we can say with 95% confidence that the difference is unlikely to be due to chance alone. In other words, we reject the null hypothesis and conclude that there is a statistically significant difference between our groups. But if the p-value is larger than 0.05, we fail to reject the null hypothesis, meaning we do not have enough evidence to say that there's a meaningful difference. Okay, I know. This got pretty far in the weeds, so here's the final too long didn't read version. In an A/B test, the t-test compares the averages of two groups, and by comparing those averages and the standard errors, it can help us determine whether the differences between those groups were likely to have occurred by chance. The lower the likelihood they occurred by chance, the more likely those groups are to be different due to our variable. In the case of the A/B test, the more likely it is the experiment worked and the B group is better and we should implement that change. Thanks all for bearing with me, and let's get back to the auditoriums. Because we're just interested in programming this though, my interns have prepared the t-test language, which is really nice and simple. It's just t.test parentheses data equals the name of your data set, and then your outcome variable or independent variable, a tilde, and then your explanatory variable or dependent variable. In practice here, this looks like t.test parentheses data equals ab underscore data, comma, converted tilde group, end parentheses. With that, let's run this and see what we get. Okay, so this output here is quite unattractive, but it has everything we need. Let's go through the relevant pieces. First thing we care about is at the bottom, the mean in group A and the mean in group B. This shows the mean in group A, our control group, is 0.101 compared to a mean of 0.156 in group B. This actually shows a bigger effect size than we might have anticipated, given that we programmed an effect size of 0.04 into the formula, but that's random sampling. That's what it does. Quick math tells us there is a 5.5% difference between the two groups, which feels like a very big change. That's really interesting and I think going to be exciting to the people at Jira Misu. So now let's look at the 95% confidence interval. We see it goes from negative 0.084 to negative 0.026, which is important because that range does not include 0. Because it doesn't include 0, it means the difference between the two groups is statistically significant. That's very exciting to us. Let's celebrate, take the win there, because now we can report back to our product team we have a clear winner, and we should be able to increase conversions between 2.5 and 8.4% here. This means big money for the people at Jira Misu, big happiness among its users, win, win, win. The third win, of course, is for us because we can claim product impact by reporting this. Finally, if we look here, we have a p-value of 0.0002, which is considerably lower than the 0.05, which is the arbitrary threshold we've set for statistical significance. This is more confirmation that our results are statistically significant, and we can be confident that the treatment group saw higher conversions than the control group. We've done a lot here. We've gone through a lot. There's been a lot going on. So let's really take a minute to take the win, be proud of what we've done. We've learned something about our product, and we can start socializing that with the Jira Misu team, letting them know what's going on. Business communication is for a different day. Keep eyes out for videos on that. But in the product world, it's time to start narrowcasting our findings, letting our stakeholders know what to expect from our ultimate share out. But that brings up a really important question. What about the share out? Do I just copy and paste that screenshot right there into my deck? Maybe an image of Scrooge McDuck diving into his money bin, everybody celebrating, maybe a gif of Tom and John Ralphio from Parks and Rec flipping money in the air. No, please don't do that. While I would find it funny if you did, I will have to take away your Dr. Chad Certified Data Viz Expert badge if I hear that you did. What should you do instead? Excellent question. Let's go back to what we've learned, our three basic graphs, and think about which one is the most appropriate for this situation. There's only two groups here we want to compare, so probably not a scatter plot. There's no linear component to it, so probably not a line graph. I think it's time for a bar graph. Meemaw used to always tell me, when in doubt, start with a bar graph, so that's what we'll do. We'll start like we always do, with a very basic bar graph just to check that we're going in the right direction. So interns, go ahead and create a basic data set to graph and then do the simplest possible bar graph for me. Okay, great. We've created a basic data frame with 2 columns and 2 rows, which will be enough for our basic graph. We went ahead and created a names column with descriptive names, control group and experimental group, because that'll be easier to graph in a minute. And then we have a column with the mean of the 2 groups taken from the t-test code earlier. Easy enough. Now, the graph. Just a simple ggplot code, data aesthetic with x of names, y of values, then geom_bar and stat equals identity. This is too easy. Let's see what it creates. Okay, this overall looks really good, if not entirely unprincipled. It does show more or less what we want it to. There's a control group, an experimental group, and a difference between the two. So now that we're happy with that, let's clean it up a bit using our 5 principles of good data viz. We won't go through it step by step, but if you haven't already, I'd strongly encourage you to watch lessons 1 and 2 in this playlist to really master those. But my interns have mastered it already, so interns, go ahead and let's see what you've done. This looks great. We have a simple graph, an honest data viz, a clear takeaway labeled in the title and the blue bar, a self-contained graph, no chart junk. I think we've got a winner here. This is a great viz that clearly illustrates what we learned and can be understood and actioned upon by anyone. I like it. Great job, everybody. Before we finish up, I want to address something very controversial in the A/B testing world: adding error bars to your graphs. A lot of people think error bars are important here to show the uncertainty in the graph, and I understand this point. It's best practices in any academic graph for sure. I disagree with this idea though, or at least say it depends on the audience you're presenting to. Here's a few reasons I think you shouldn't present your error bars. Number 1, they're misleading without context. Stakeholders unfamiliar with statistics might misinterpret error bars as representing variability in the data, e.g. a standard deviation, rather than uncertainty about the means, e.g. a standard error or confidence intervals. This can lead to confusion about what the graph is actually showing. Point number 2, stakeholders often care about trends, not uncertainty. In the product world, you're looking for action-oriented decisions, and stakeholders typically care about whether one group performs better than another. Did this new feature increase conversions? Rather than the precise uncertainty around those results. A bar graph without error bars makes it easier to highlight trends and differences between groups without introducing statistical complexity. Number 3, error bars can overcomplicate visuals. If you've watched my other videos, you know I'm a big fan of the Coco Chanel test. And adding error bars can make a graph look busy, particularly if there are multiple groups or overlapping intervals. This can reduce clarity and make it much harder for stakeholders to quickly grasp that main point. A simple bar graph with clear labels and annotations can often communicate your findings more effectively to a non-technical audience. Number 4, there are other, better ways to communicate uncertainty. If uncertainty is important to your message, you can explain it more intuitively. One good way is annotations or text, so instead of showing error bars, include a brief note or call out in the graph somewhere, something like, results are statistically significant at p less than 0.05. You can also use confidence statements, so in your presentation report, you can say things like, we are 95% confident the new feature increased conversions by 5 to 7%. It's not quite precise enough, and stats nerds, don't yell at me. But for technical stakeholders, that's good enough. You can also have supplementary materials where we provide detailed statistical results in an appendix somewhere. For me, the downside to adding error bars is far greater than any upside you get when you're talking to stakeholders who aren't familiar with statistics. All that being said, you're going to see me in the auditorium in a minute finish by walking through how to calculate the 95% confidence interval, how to graphic, but I did want to bring these issues to the surface for anyone who's interested. What do you all think? Make sure you comment on this video, tell me I'm wildly wrong, I'm amazingly right and super smart. Whichever way, I'd love to hear from you. So, jump in the comments and let me know. Thanks all, and back to the auditorium one last time. So we have one more final step here, and that's to calculate a 95% confidence interval around our estimate so we can show our stakeholders the statistical uncertainty that comes with this sort of test. Transparency is important, and as stats people, we need to be completely transparent with our stakeholders when communicating statistical concepts. There's a few ways to calculate the confidence intervals, the first being to do a t-test for each group individually using code my interns have right here. Lines 1 and 3 filter the AB data by their groups, and then lines 2 and 4 run t-tests on each group individually with a null hypothesis of converted is not equal to 0. R will show you the 95% confidence interval in each of these calculations, and then you can use those in your bar graphs later. There's another way to do it by using the dplyr or summarize function, then doing a bunch of calculations by hand. Interns, go ahead and show that here if you can. Perfect, yeah. We're showing this for completeness, and maybe ease if you have a large number of groups. Either way though, we get the same result, so it's really just a matter of personal preference. What I'm going to do right now is add the 95% confidence interval values to our graph, first by adding the values to the data frame. So interns, show us how to set up those data. Simple enough, right? We create a new variable called lower CI and give it values of 0.82 and 0.133. That represents the lower bound of the confidence interval for both groups, the control and experimental group. Then we do the same for upper CI with values of 0.1197 and 0.1785, representing the upper bound of the confidence interval, again, for both groups. The interns are going to go ahead one more time and run this and show what we get. Look at that. There they are. We have error bars. I know I presented a case for and against error bars, but if you're going to add them, I do recommend explaining what they mean in a caption. So I actually want to do one more line of code here. Your stakeholders probably aren't as familiar with this as they should be or you'd like them to be, so go ahead and explain it. It's really important to be transparent and do it well. Captions to a plot go in the labs layer and is as simple as typing labs, parentheses, caption equals, and then whatever your caption is, followed by end parentheses. In this case, we'll have it say error bars represent 95% confidence intervals. Differences are statistically significant at p is less than 0.05. Once we run that, we'll see the final output. Okay, this looks great. Now that we're done, let's go through our checklist one more time before we end the video to make sure we have a principled data visualization. Number 1, we use simple data viz here. Check. Number 2, we're honest with our data viz. Check. Number 3, we clearly highlight the important takeaways. Check. The graph is self-contained. Yeah, I wouldn't need anything else to understand this. Check. The graph would impress Coco Chanel, the most important one. And we get a check for this. Although the error bars and captions seem a bit much to me, reasonable people can disagree. This is great though. We've performed our first A/B test, we've visualized it for a deck to share with stakeholders so they can make easy decisions. Most importantly though, this is a great example of a bivariate analysis. We looked at two things by group. We looked at an A group and a B group, a control group and an experimental group. And from there, we made a comparison using a very simple, principled, elegant bar graph. We did a lot of work today. I'm impressed and proud of everyone. Great job, and we'll see you next time as we get into some multivariate analyses. Thanks, everybody.